Self-induction of continuous current circuits. Self-induction makes itself felt in continuous current circuits only in starting and stopping, or in general changing the current. Starting of current. If R equals resistance, L equals inductance of circuit, E equals continuous electromotive force impressed upon the circuit, I equals current in the circuit at time t after impressing the electromotive force E, and di the increase of current during the time moment dt, then the increase of magnetic interlinkages during time dt is L times di. The electromotive force induced thereby is E1 equals negative L times di by dt, negative since opposite to the impressed electromotive force as its cause by Lenz's law. Thus, the electromotive force acting in this moment upon the circuit is E plus E equals E minus L di by dt, and the current I equals E plus E1 over R equals E minus L di by dt, all over R. Transposed, negative R dt over L equals di over the quantity I minus E over R, the integral of which is negative RT over L equals natural log of quantity I minus E over R minus natural log of C, where C is the integration constant. This reduces to I equals E over R plus C times E to the power negative RT over L. At t equals 0, I equals 0, and thus negative E over R equals C. Substituting this value, I equals E over R times the quantity 1 minus E to the power negative RT over L, the current, E1 equals I R minus E equals negative E to the power negative RT over L, the electromotive force of self-induction. At t equals infinity, I naught equals E over R and E1 equals 0. Substituting these values, I equals I naught times the quantity 1 minus E to the power negative RT over L, E1 equals negative Ri naught E to the power negative RT over L. The expression T naught equals L over R is called the time constant of the circuit. Substituted in the foregoing equation, this gives I equals E over R times the quantity 1 minus E to the power negative T over T naught, and E1 equals negative E to the power negative T over T naught. At t equals t naught, E1 equals negative E over E, which is negative 0.368 E. Stopping of current. In a circuit of inductance L and resistance R, let A current I naught equals E over R be produced by the impressed electromotive force E, and this electromotive force E be withdrawn and the circuit closed by a resistance R1. Let the current be I at the time t after withdrawal of the electromotive force E, and the change of current during time moment dt be di. di is negative, that is, the current decreases. The decrease of magnetic interlinkages during moment dt is LDI. Thus, the electromotive force induced thereby E1 equals negative LDI by dt, negative since di is negative, and E1 must be positive or in the same direction as E to maintain the current or oppose the decrease of current as its cause. The current is then I equals E1 over R plus R1 equals negative L over R plus R1 times di by dt. Or transposed, negative R plus R1 over L times dt equals di over I, the integral of which is negative R plus R1 over L times t equals natural log I minus natural log C. This reduces to I equals C e to the power negative R plus R1 times t over L. For t equals 0, I naught equals E over R equals C. Substituting this value, we have I equals E over R e to the power negative R plus R1 times t over L, the current, E1 equals I times the quantity R plus R1 equals E times R plus R1 over R, e to the power negative R plus R1 times T over L, the induced electromotive force. Substituting I naught equals E over R, we have I equals I naught e to the power negative R plus R1 times T over L, the current, E1 equals I naught times the quantity R plus R1, e to the power negative R plus R1 times T over L, the induced electromotive force. At t equals 0, E1 equals I naught times the quantity R plus R1 equals E times R plus R1 over R. That is, the induced electromotive force is increased over the previously impressed electromotive force in the same ratio as the resistance is increased. When R1 equals 0, that is, when in withdrawing the impressed electromotive force E, the circuit is short-circuited, I equals E over R e to the power negative RT over L, the current, and E1 equals E to the power negative RT over L, the induced electromotive force. In this case, at t equals 0, E1 equals E, that is, the electromotive force does not rise. In the case R equals infinity, that is, if in withdrawing the electromotive force E, the circuit is broken, we have at t equals 0, E1 equals infinity, that is, the electromotive force rises infinitely. The greater R1, the higher is the induced electromotive force E1. The faster, however, E and I decrease. If R1 equals R, we have at t equals 0, E1 equals 2E, and the terminal voltage at the moment of withdrawal equals E. The effect of the electromotive force self-induction in stopping the current is, at the time t, the instantaneous power I1 equals I naught squared times the quantity R plus R1, e to the power negative 2 times R plus R1 times t over L. Thus, the total energy of the induced electromotive force is W equals the integral from 0 to infinity of IE1 dt equals I naught squared times the quantity r plus r1 times the integral of e to the power negative 2 times r plus r1 times t over L with respect to t, which gives I naught squared times L over 2. That is, the energy stored as magnetism in a circuit of current I naught and self-inductance L is W equals I naught squared L over 2, which is independent both of the resistance R of the circuit and the resistance R1 inserted in breaking the circuit. This energy has to be expended in stopping the current. Examples. 1. In the alternator field in section 1, example 4, section 2, example 2, and section 5, example 1. How long time after impressing the required electromotive force of 230 volts will it take for the field to reach half strength and 9/10 strength? 2. If 500 volts are impressed upon the field of this alternator and a non-inductive resistance inserted in series so as to give the required exciting current of 6.95 amperes, how long after impressing the electromotive force of 500 volts will it take for the field to reach half strength, 9/10 strength, and what is the resistance required in the rheostat? If 500 volts are impressed upon the field of this alternator without insertion of resistance, how long will it take for the field to reach full strength? 4. With full field strength, what is the energy stored as magnetism? 1. The resistance of the alternator field is 38.2 ohms, the inductance 112 henries. With impressed electromotive force 230, the final value of current I naught equals E over R equals 6.95 amperes. Thus, the current at time t is I equals I naught times 1 minus e to the power negative RT over L, or I equals 6.95 times 1 minus e to the power negative 0.34 t. A. For half strength, I equals I naught over 2 equals 3.475. Hence, 1 minus e to the power negative 0.34 t equals 0.5. Therefore, e to the power negative 0.34 t equals 0.5. Taking logs, negative 0.34 t equals log 0.5 equals negative 0.693. Thus, t equals 0.693 over 0.34 equals 2.34 seconds. B. For 9/10 strength, I equals 0.9 I naught. Hence, 1 minus e to the power negative 0.34 t equals 0.9. So e to the power negative 0.34 t equals 0.1. Then negative 0.34 t equals log 0.1 equals negative 2.30. Thus, t equals 2.30 over 0.34 equals 7.8 seconds. 2. To get I naught equals 6.95 amperes with electromotive force 500 volts, a resistance R equals 500 over 6.95 equals 72 ohms, and thus a rheostat of 72 minus 38.2 equals 38.8 ohms is required. We then have I equals I naught times 1 minus e to the power negative RT over L equals 6.95 times 1 minus e to the power negative 0.648 t. A. For half strength, I equals I naught over 2, hence t equals 1.08 seconds. B. For 9/10 strength, t equals 3.6 seconds. 3. Impressing 500 volts upon a circuit of R equals 38.2, L equals 112 gives I equals E over R times 1 minus e to the power negative RT over L equals 13.1 times 1 minus e to the power negative 0.34 t. For full field strength, 6.95 equals 13.1 times 1 minus e to the power negative 0.34 t. Then 1 minus e to the power negative 0.34 t equals 0.53. Thus, e to the power negative 0.34 t equals 0.46. So negative 0.34 t equals log 0.46 equals negative 0.77. T equals 0.77 over 0.34 equals 2.08 seconds. 4. The stored energy equals I naught squared L over 2 equals 6.95 squared times 112 over 2 equals 2720 watt seconds or joules equals 2,000 foot-pounds. Thus, in case 3, where the field reaches full strength in 2.08 seconds, the average power input is 2,000 over 2.08 equals 960 foot-pound seconds, equals 1.8 horsepower. In breaking the field circuit of this alternator, 2,000 foot-pounds have to be destroyed in the spark, and so on. 5. A coil of resistance R equals 0.002 ohms, and inductance L equals 0.005 henries, carrying current I equals 90 amperes, is short-circuited. A. What is the equation of the current after short circuit? B. In what time has the current decreased to 1/10 its initial value? A. I equals I e to the power negative RT over L equals 90 e to the power negative 400t. B. For 1/10 value, I equals 0.1, I equals 9. So e to the power negative 400t equals 0.1. Then negative 400t equals log 0.1 equals negative 2.30. T equals 0.00576 seconds. 6. When short-circuiting the coil in example 5, an electromotive force of 1 volt is inserted in the circuit of this coil in opposite direction to the current. A. What is the equation of the current? B. After what time has the current become 0? C. After what time has the current reverted to its initial value in opposite direction? D. What impressed electromotive force is required to make the current die out in 1/3000th second? E. What impressed electromotive force is required to reverse the current in 1/3000th second? A. If electromotive force equals negative E is inserted, and at time t the current is denoted by I, we have E1 equals negative L di by dt, the induced electromotive force. Thus, negative E plus E1 equals negative E minus L di by dt, the total electromotive force. And I equals negative E plus E1 over R equals negative E over R minus L over R times di by dt. Transposed negative R over L dt equals di over E over R plus I. Integrated, negative RT over L equals natural log of the quantity E over R plus I minus natural log of C, where C is the integration constant. At t equals 0, I equals I, thus C equals I plus E over R. Substituted I equals the quantity I plus E over R, e to the power negative RT over L minus E over R equals 590 e to the power negative 400t minus 500. B, for I equals 0, 0 equals 590 e to the power negative 400t minus 500. Thus, e to the power negative 400t equals 0.85 after t equals 0.0004 seconds. C, for I equals negative I equals negative 90, we have negative 90 equals 590 e to the power negative 400t minus 500. Thus, e to the power negative 400t equals 0.694 after t equals 0.0009 seconds. D, if I equals 0 at t equals 0.000333, then 0 equals 90 plus 500e times e to the power negative RT over L minus 500e. So 500e times e to the power negative 0.133 minus 500e equals negative 90. Then e equals 0.18 over 1 minus e to the power negative 0.133 equals 0.81 volts. E, if I equals negative 90 at t equals 0.001, then negative 90 equals 90 plus 500e times e to the power negative 0.4 minus 500e. Thus, E equals 0.18 times 1 plus e to the power negative 0.4 over 1 minus e to the power negative 0.4 equals 0.91 volts. Section 7. Self-induction in alternating current circuits. An alternating current I equals I naught sine 2 pi nt, or I equals I naught sine phi, can be represented graphically in rectangular coordinates by a curved line as shown in figure 6, with the instantaneous values I as ordinates and the time t, or the arc of the angle corresponding to the time, phi equals 2 pi nt, as abscissa, counting the time from the zero value of the rising wave as 0 point. If the zero value of current is not chosen as 0 point of time, the wave is represented by I equals I naught sine 2 pi n times the quantity t minus t naught, or I equals I naught sine phi minus phi naught, where t equals t naught or phi equals phi naught, is the time and the corresponding angle at which the current reaches its zero value in the ascendant. If such a sine wave of alternating current, I equals I naught sine 2 pi nt, or I equals I naught sine phi, passes through a circuit of resistance R and inductance L, the magnetic flux produced by the current, and thus its interlinkages with the current, IL equals I naught L sine phi, vary in a waveline similar also to that of the current, as shown in figure 7 as phi. The electromotive force induced hereby is proportional to the change of IL, and is thus a maximum where IL changes most rapidly, or at its 0 point, and 0 where IL is a maximum. It is positive during falling, negative during rising current, by Lenz's law. Thus, this induced electromotive force is a wave following the wave of current by the time t equals t over 4, where t is the time of one complete period equals 1 over n, or by the angle phi equals 90 degrees. This electromotive force is called the counter-electromotive force of self-induction. It is E prime equals negative L di by dt equals negative 2 pi NL I naught cosine 2 pi nt. It is shown in dotted line in figure 7 as E prime. The quantity 2 pi NL is called the reactance of the circuit and denoted by X. It is of the nature of a resistance and expressed in ohms. If L is given in 10 to the power 9 absolute units or henries, X appears in ohms. The counter-electromotive force of self-induction of current I equals I naught sine 2 pi nt equals I naught sine phi of effective value I equals I naught over square root 2 is E prime equals negative x I naught cosine 2 pi nt equals negative x I naught cosine phi of maximum value xi naught and effective value E2 equals xi. That is, the effective value of the counter-electromotive force of self-induction equals the reactance X times the effective value of the current I and is lagging 90 degrees, or a quarter period, behind the current. By the counter-electromotive force of self-induction, E prime equals negative xi naught cosine phi, which is induced by the passage of the current I equals I naught sine phi through the circuit of reactance X, an equal but opposite electromotive force, E2 equals xi naught cosine phi, is consumed and thus has to be impressed upon the circuit. This electromotive force is called the electromotive force consumed by self-induction. It is 90 degrees, or a quarter period ahead of the current, and shown in figure 7 as drawn line E2. Thus, we have to distinguish between counter-electromotive force of self-induction, 90 degrees lagging, and electromotive force consumed by self-induction, 90 degrees leading. These electromotive forces stand in the same relation as action and reaction in mechanics. They are shown in figure 7 as E2 and as E prime. The electromotive force consumed by the resistance R of the circuit is proportional to the current, E1 equals Ri naught sine phi, and in phase therewith, that is, reaches its maximum and its zero value at the same time as the current I, as shown by drawn line E1 in figure 7. Its effective value is E1 equals Ri. The resistance can also be represented by a fictitious counter-electromotive force, E1 prime equals negative Ri naught sine phi, opposite in phase to the current, shown as E1 prime in dotted line in figure 7. The counter-electromotive force of resistance and the electromotive force consumed by resistance have the same relation to each other as the counter-electromotive force of self-induction and the electromotive force consumed by self-induction or reactance. If an alternating current I equals I naught sine phi of effective value, I equals I naught over square root 2 passes through a circuit of resistance R and inductance L, that is, reactance X equals 2 pi NL, we have thus to distinguish. Electromotive force consumed by resistance, E1 equals Ri naught sine phi, of effective value E1 equals Ri, and in phase with the current. Counter-electromotive force of resistance, E1 prime equals negative Ri naught sine phi, of effective value E1 prime equals Ri, and in opposition, or 180 degrees, displaced from the current. Electromotive force consumed by reactance, E2 equals xi naught cosine phi, of effective value E2 equals xi, and leading the current by 90 degrees or a quarter period. Counter-electromotive force of reactance, E2 prime equals negative xi naught cosine phi, of effective value E2 prime equals xi, and lagging 90 degrees or a quarter period behind the current. The electromotive The electromotive forces consumed by resistance and by reactance are the electromotive forces which have to be impressed upon the circuit to overcome the counter-electromotive forces of resistance and of reactance. The total counter-electromotive force of the circuit is thus E prime equals E1 prime plus E2 prime equals negative I naught times the quantity R sine phi plus X cosine phi. And the total impressed electromotive force, or electromotive force consumed by the circuit, E equals E1 plus E2 equals I naught times the quantity R sine phi plus X cosine phi. Substituting X over R equals tangent omega and square root of R squared plus X squared equals Z, from which follow X equals Z sine omega and R equals Z cosine omega, we have total impressed electromotive force E equals I naught Z sine phi plus omega, shown by heavy drawn line E in figure 7, and total counter-electromotive force E prime equals negative Z I naught sine phi plus omega, shown by heavy dotted line E prime in figure 7, both of effective value E equals Z I. For phi equals negative omega, E equals 0, that is, the zero value of E is by angle omega ahead of the zero value of current, or the current lags behind the impressed electromotive force by angle omega. Omega is called the angle of lag of the current, and Z equals square root of R squared plus X squared, the impedance of the circuit. E is called the electromotive force consumed by impedance, E prime the counter-electromotive force of impedance. Since E1 equals Ri is the electromotive force consumed by resistance, and E2 equals Xi is the electromotive force consumed by reactance, and E equals Zi equals square root of E1 squared plus E2 squared, is the electromotive force consumed by impedance, we have E equals square root of E1 squared plus E2 squared, the total electromotive force, and E1 equals E cosine omega, E2 equals E sine omega, its components. The tangent of the angle of lag is tangent omega equals X over R equals 2 pi n L over R. And the time constant of the circuit is L over R equals tangent omega over 2 pi n. The total electromotive force impressed upon the circuit E consists of two components, one, E phi, in phase with the current, the other EQ in quadrature with the current. Their effective values are E1 equals E cosine omega, E2 equals E sine omega. Examples. 1. What is the reactance per wire of a transmission line of length L if D equals diameter of the wire, D equals distance between wires, and N equals frequency? If I equals current in absolute units in one wire of the transmission line, the magnetomotive force is I. Thus, the magnetizing force in a zone dx at distance x from center of wire, as in figure 8, is F equals I over 2 pi x, and the field intensity in this zone is H equals 4 pi F equals 2I over x. Thus, the magnetic flux in this zone is d phi equals HL dx equals 2IL dx over x. Hence, the total magnetic flux between the wire and the return wire, neglecting the flux inside the transmission wire, is phi equals the integral from d over 2 to d over 2 of d phi, equals 2IL times the integral from d over 2 to d over 2 of dx over x, equals 2IL log natural of 2d over d. The coefficient of self-induction, or inductance, is thus L equals phi over I equals 2L log natural of 2d over d absolute units, equals 2L log natural of 2d over d times 10 to the minus 9 henries, and the reactance X equals 2 pi n L equals 4 pi n L log natural of 2d over d absolute units, equals 4 pi n L log natural of 2d over d times 10 to the minus 9 ohms. 2. The voltage at the receiving end of a 33.3 cycle transmission of 14 miles length shall be 5500 between the lines. The transmission consists of 3 wires, number naught B and SG, diameter equals 0.82 centimeters, 18 inches apart, that is 45 centimeters. Resistivity rho equals 1.8 times 10 to the minus 6. A. What is the resistance, the reactance, and the impedance per line, and the voltage consumed thereby at 44 amperes flowing over the line? B. What is the generator voltage between lines at 44 amperes flowing into a non-inductive circuit? C. What is the generator voltage between lines at 44 amperes flowing into a circuit of 45 degrees lag? D. What is the generator voltage between lines at 44 amperes flowing into a circuit of 45 degrees lead? Here, L equals 14 miles equals 14 times 1.6 times 10 to the 5th equals 2.23 times 10 to the 6th centimeters. D equals 0.82 centimeters. Hence, section S equals 0.528 square centimeters. D equals 45. N equals 33.3. A. Resistance per line. R equals rho L over S equals 1.8 times 10 to the minus 6 times 2.23 times 10 to the 6th over 0.528 equals 7.60 ohms. Reactance per line. X equals 4 pi NL log natural of 2D over D times 10 to the minus 9 equals 4 pi times 33.3 times 2.23 times 10 to the 6th times log natural of 100 times 10 to the minus 9 equals 4.35 ohms. The impedance per line Z equals square root of R squared plus X squared equals 8.76 ohms. Thus, if I equals 44 amperes effective per line, electromotive force consumed by resistance E1 equals Ri equals 334 volts. Electromotive force consumed by reactance E2 equals Xi equals 192 volts. Electromotive force consumed by impedance E3 equals Zi equals 385 volts. Or B. 5500 volts between lines at receiving circuit gives 5500 over square root 3 equals 3170 volts between line and neutral or 0 point, as in figure 9. Per line, this corresponds to a maximum voltage of 3180 times square root 2 equals 4500 volts. 44 amperes effective per line gives a maximum value of 44 times square root 2 equals 62 amperes. Denoting the current by I equals 62 sine phi, the voltage per line at the receiving end with non-inductive load is E equals 4500 sine phi. The electromotive force consumed by resistance in phase with the current of effective value 384, thus maximum value 384 times square root 2 equals 472, is E1 equals 472 sine phi. The electromotive force consumed by reactance 90 degrees ahead of the current of effective value 192, thus maximum value 272 is E2 equals 272 cosine phi. Thus the total voltage required at the generator end of the line is per line E0 equals E plus E1 plus E2 equals the quantity 4500 plus 472 times sine phi plus 272 cosine phi equals 4972 sine phi plus 272 cosine phi. Denoting 272 over 4,972 equals tangent beta. We have sine beta equals tangent beta over square root of 1 plus tangent squared beta equals 272 over 4,980. Cosine beta equals 4,972 over 4,980. Hence, E0 equals 4,980 times the quantity sine phi cosine beta plus cosine phi sine beta equals 4,980 sine of phi plus beta. Thus, beta is the lag of the current behind the electromotive force at the generator end of the line equals 3.2 degrees and 4,980 the maximum voltage per line at the generator end. Thus, E0 equals 4,980 over square root 2 equals 3,520 effective per line. And 3,520 times square root 3 equals 6,100 effective voltage between lines at the generator. C. If the current I equals 62 sine phi, lags 45 degrees behind the electromotive force at the receiving end. This electromotive force is expressed by E equals 4,500 sine of phi plus 45 degrees, equals 3,170 times the quantity sine phi plus cosine phi. The electromotive force consumed by resistance and by reactance being the same as in part B, the generator voltage per line is E0 equals E plus E1 plus E2 equals 3,642 sine phi plus 3,442 cosine phi. Denoting 3,442 over 3,642 equals tangent beta, we have E0 equals 5,011 sine of phi plus beta. Thus beta, the angle of lag of the current behind the generator electromotive force, is 43 degrees and 5,011 the maximum voltage. Hence, 3,550 the effective voltage per line, and 3,550 times square root 3 equals 6,160 the effective voltage between lines at the generator. D, if the current I equals 62 sine phi leads the electromotive force by 45 degrees, the electromotive force at the receiving end is E equals 4,500 sine of phi minus 45 degrees equals 3,170 times the quantity sine phi minus cosine phi. Thus, at the generator end, E0 equals E plus E1 plus E2 equals 3,642 sine phi minus 2,898 cosine phi. Denoting 2,898 over 3,642 equals tangent beta, it is E0 equals 4,654 sine of phi minus beta. Thus, beta, the angle of lead at the generator, is 39 degrees, and 4,654 the maximum voltage, hence 3,290 the effective voltage per line, and 5,710 the effective voltage between the lines at the generator. Effect of alternating currents. The effect or power consumed by alternating current I equals I0 sine phi of effective value I equals I0 over square root 2 in a circuit of resistance R and reactance X equals 2 pi N L is P equals EI, where E equals ZI naught sine the quantity phi, plus omega is the impressed electromotive force, consisting of the components E1 equals R I naught sine phi, the electromotive force consumed by resistance, and E2 equals Xi naught cosine phi, the electromotive force consumed by reactance, and Z equals square root of R squared plus X squared is the impedance. Tangent omega equals X over R, the phase angle of the circuit. The effect is thus P equals Z I naught squared over 2 sine phi sine the quantity phi plus omega equals Z I naught squared over 2 times the quantity cosine omega minus cosine 2 phi plus omega equals Z I squared times the quantity cosine omega minus cosine the quantity 2 phi plus omega. Since the average of cosine the quantity 2 phi plus omega is 0, the average effect is P equals Zi squared cosine omega equals Ri squared equals E1I. That is, the effect of the circuit is that consumed by the resistance and independent of the reactance. Reactance or self-induction consumes no effect, and the electromotive force of self-induction is a Wattless electromotive force, while electromotive force of resistance is an energy electromotive force. The Wattless electromotive force is in quadrature, the energy electromotive force in phase with the current. In general, if omega equals phase angle of circuit, I equals current. E equals impressed electromotive force, consisting of two components, one equals E cosine omega, in phase with the current, the other E2 equals E sine omega, in quadrature with the current. The effect of the circuit is E1 equals I cosine omega, and the electromotive force in phase with the current E1 equals E cosine omega is an energy electromotive force. The electromotive force in quadrature with the current E2 equals E sine omega, a Wattless electromotive force. Thus, we have to distinguish energy electromotive force and Wattless electromotive force, or energy component of electromotive force in phase with the current and Wattless component of electromotive force in quadrature with the current. Any electromotive force can be considered as consisting of two components, one in phase with the current, or energy electromotive force, E1, and one in quadrature with the current, or Wattless electromotive force, E2. The sum of instantaneous values of the two components is the total electromotive force, E equals E1 plus E2. If E, E1, E2 are the respective effective values, we have E equals square root of E1 squared plus E2 squared, since E1 equals E cosine omega, E2 equals E sine omega, where omega equals phase angle between current and electromotive force. Analogously, a current I passing through a circuit of impressed electromotive force E with phase angle omega can be considered as consisting of two component currents. I1 equals I cosine omega, the energy current or energy component of current, and I2 equals I sine omega, the Wattless current or Wattless component of current. The sum of instantaneous values of energy and of Wattless currents equals the instantaneous value of total current, I1 plus I2 equals I, while their effective values have the relation I equals square root of I1 squared plus I2 squared. Thus, an alternating current can be resolved in two components, energy current in phase and Wattless current in quadrature with the electromotive force. An alternating electromotive force can be resolved in two components, energy electromotive force in phase and Wattless electromotive force in quadrature with the current. The effect of the circuit is the current times the electromotive force times the cosine of the phase angle, or is the energy current times the total electromotive force, or the energy electromotive force times the total current. Examples. 1. What is the effect received over the transmission line in section 7? Example 2, the effect lost in the line, the effect put into the line, and the efficiency of transmission with non-inductive load, 45 degrees lag, and 45 degrees lid. The effect received per line at non-inductive load is P equals E, I equals 3,170 times 44 equals 137 kilowatts. On load of 45 degrees phase displacement, P equals EI over cosine 45 equals 97 kilowatts. The effect lost per line, P1 equals I squared R, equals 44 squared times 7.6 equals 14.7 kilowatts. Thus, the input into the line P0 equals P plus P1 equals 151.7 kilowatts at non-inductive load and equals 111.7 kilowatts at load of 45 degrees phase displacement. The efficiency is with non-inductive load, P over P0 equals 1 minus 14.7 over 151.7 equals 90.3%. With load of 45 degrees phase displacement, P over P0 equals 1 minus 14.7 over 111.7 equals 86.8%. The total output 3P equals 411 kilowatts and 291 kilowatts, respectively. The total input 3 P naught equals 451.1 kilowatts and 335.1 kilowatts respectively. Section 9. Polar coordinates. In polar coordinates, alternating waves are represented with the instantaneous values as radii vectors and the time as angle, counting left-handed or counterclockwise, and 1 revolution or 360 degrees, representing 1 complete period. The sine wave of alternating current I equals I naught sine phi is represented by a circle, figure 10, with the vertical axis as diameter, equal in length OI naught to the maximum value I naught, and shown as heavy drawn circle. The electromotive force consumed by self-induction, E2 equals xi naught cosine phi, is represented by a circle with diameter O E2 in horizontal direction to the right and equal in length to the maximum value xi naught. Analogously, the counter-electromotive force of self-induction, E2 prime, is represented by a circle OE2 prime in figure 10. The electromotive force consumed by resistance R by circle OE1 of a diameter equals E1 equals Ri naught. The counter-electromotive force of resistance E1 prime by circle OE1 prime. The counter-electromotive force of impedance is represented by circle OE prime of a diameter equal in length to E prime and lagging 180 minus omega behind the diameter of the current circle. This circle passes through the points E1 prime and E2 prime, since at the moment phi equals 180 degrees, E1 prime equals 0, and thus the counter-electromotive force of impedance equals the counter-electromotive force of reactance, E2 prime equals E2 prime, and at phi equals 270 degrees, E2 prime equals 0, and the counter-electromotive force of impedance equals the counter-electromotive force of resistance, E1 prime equals E1 prime. The electromotive force consumed by impedance, or impressed electromotive force, is represented by circle OE of a diameter equal in length to E, and leading the diameter of the current circle by angle omega. This circle passes through the points E1 and E2. An alternating wave is determined by the length and direction of the diameter of its polar circle. The length is the maximum value or intensity of the wave, the direction, the phase of the maximum value, generally called the phase of the wave. Usually alternating waves are represented in polar coordinates by mere vectors, the diameters of their polar circles and the circles omitted, as in figure 11. Two electromotive forces, E1 and E2, acting in the same circuit, give a resultant electromotive force, E equal to the sum of their instantaneous values. In polar coordinates, E1 and E2 are represented in intensity and in phase by two vectors, OE1 and OE2, figure 12. The instantaneous values in any direction OX are the projections OC1, OC2 of OE1 and OE2 upon this direction. Since the sum of the projections of the sides of a parallelogram is equal to the sum of their instantaneous values, the diagonal OE of the parallelogram with OE1 and OE2 as sides is thus the diameter of the circle of resultant electromotive force. That is, in polar coordinates, alternating sine waves of electromotive force, current, etc., are combined and resolved by the parallelogram or polygon of sine waves. Since the effective values are proportional to the maximum values, the former are generally used as the length of vector of the alternating wave. In this case, the instantaneous values are given by a circle with square root of 2 times the vector as diameter. As phase of the first quantity considered, as in the above instance, the current, any direction can be chosen. The further quantities are determined thereby in direction or phase. In polar coordinates, as phase of the current, etc., is here, and in the following understood the time or the angle of its vector, that is, the time of its maximum value, and a current of phase 0 would thus be denoted analytically by I equals I naught cosine phi. The zero vector OA is generally chosen for the most frequently used quantity or reference quantity, as for the current, if a number of electromotive forces are considered in a circuit of the same current, or for the electromotive force, if a number of currents are produced by the same electromotive force, or for the induced electromotive force in induction apparatus, as transformers and induction motors, or for the counter-electromotive force in synchronous apparatus, etc. With the current as zero vector, all horizontal components of electromotive force are energy electromotive forces. All vertical components are wattless electromotive forces. With the electromotive force as zero vector, all horizontal components of current are energy currents. All vertical components of currents are wattless currents. By measurement from the polar diagram, numerical values can hardly ever be derived with sufficient accuracy, since the magnitude of the different quantities entering the same diagram is usually by far too different, and the polar diagram is therefore useful only as basis for trigonometrical or other calculation, and to give an insight into the mutual relation of the different quantities, And even then, great care has to be taken to distinguish between the two equal but opposite vectors. Counter-electromotive force and electromotive force consumed by the counter-electromotive force, as explained before. Examples. In a three-phase long-distance transmission, the voltage between lines at the receiving end shall be 5,000 at no load, 5,500 at full load of 44 amperes energy current, and proportional at intermediary loads, that is 5,250 at three-quarter load, etc. At three-quarter load, the current shall be in phase with the electromotive force at the receiving end. The generator excitation, and thus the nominal induced electromotive force of the generator, shall be maintained constant at all loads. The line has the resistance R1 equals 7.6 ohms and the reactance X1 equals 4.35 ohms per wire. The generator in Y connection per circuit, the resistance R2 equals 0.71 and the synchronous reactance X2 equals 25 ohms. What must be the current and its phase relation at no load, at quarter load, at half load, at three-quarter load, and full load, and what will be the terminal voltage of the generator under these conditions? The total resistance of the circuit is R equals R1 plus R2 equals 8.31 ohms. The total reactance X equals X1 plus X2 equals 29.35 ohms. Let, in the polar diagram, figure 13 or 14, OE equals E, represent the voltage at the receiving end of the line. OI1 equals I1, the energy current corresponding to the load, in phase with OE. And OI2 equals I2, the wattless current, in quadrature with OE, shown leading in figure 13, lagging in figure 14. We then have total current I equals OI. Thus, electromotive force consumed by resistance E1 equals RI1 in phase with I. Electromotive force consumed by reactance E2 equals XI2, 90 degrees ahead of I, and their resultant THIF, the electromotive force consumed by impedance OEX combined with OE, the receiving voltage, gives the generator voltage OEG. Resolving all electromotive forces and currents in components in phase and quadrature with the received voltage E, we have phase component, current I1, quadrature component, current I2, electromotive force at receiving end of line, E and 0. Electromotive force consumed by resistance, E1 equals RI1 and RI2. Electromotive force consumed by reactance, E2 equals XI2 and negative XI1. Thus, total electromotive force or generator voltage, EG equals E plus E1 plus E2 equals E plus RI1 plus XI2 plus quantity RI2 minus XI1. Herein, the wattless lagging current is assumed as positive, the leading as negative. The generator electromotive force thus consists of two components, which give the resultant value EG equals square root of the quantity E plus RI, 1 plus XI2 squared, plus the quantity RI2 minus XI1 squared. Substituting in numerical values, this becomes EG equals square root of the quantity E plus 8.31 I1 plus 29.35 I2 squared, plus the quantity 8.31 I2 minus 29.35 I1 squared. At three-quarter load, it is E equals 5375 over square root 3 equals 3090 volts per circuit, I1 equals 33, I2 equals 0. Thus, EG equals square root of the quantity 3090 plus 8.31 times 33 squared plus negative 29.35 times 33 squared equals 3520 volts per line, or 3520 times square root 3 equals 6,100 effective volts between lines at generator as nominal induced electromotive force of generator. The voltage between the lines at receiving end shall be